name came from. So we've been looking at this, and this is a hard problem in part because development productivity is not easy to measure. There are no accepted standards. I mean, system performance is hard to measure. Development productivity is much harder. But there's a whole effort being kicked off that some academic groups are involved in to actually formalize development productivity, and we're going to use that as our reference point. What we are doing, just to set the context, is that we see two dimensions to improving productivity. The horizontal dimension is what we call reducing the expertise gap, and that's basically making programming of these systems accessible to a larger community. And the issue over here is when we go to any of these organizations that have this machine, they might have an organization of 500 software engineers. Only 10 of them, if you're lucky, really understand the full system, what the compiler and the OS do. And the others cannot really contribute productively. So we're looking at ways to make them productive. And the vertical dimension is accelerating the software development life cycle, which means get their programming tasks and the whole software life cycle tasks completed more quickly. There are concrete projects happening in each of these areas, and I wish I had time to talk about all of them. The Eclipse-based tools which use refactoring to say that if you don't need to be an expert in concurrent programming, the refactoring will guide you. There's component-based development. One of our university partners is building a tool for extracting components from legacy Fortran code, and so that they can be made callable. There's this morphogenic software, which is really our separation of concerns effort. We have an open source Eclipse project called Concern Manipulation Environment. There's also work done at one of our partners in Berkeley on separating the role between performance tuning and algorithm specification and streaming applications. Extend, what I'm going to talk about, and this visualization, validation, verification, the P2 tool that you heard about from Evelyn is part of that topic. Okay, so enough of context. Let's get to Extend. Oh, I should say there was a lot of discussion. Do we need, does anyone need to do parallel programming? And the point is, we're not saying that new model for parallel programming is the full answer. That's the whole point of this context. But you definitely need improvements in the parallel programming model. I don't know what's the right analogy to make this point. I was thinking of transportation. It's like saying, do you need improvements in aircraft control and guidance if most people drive cars? Well, yes, you do, to make transport. So it's kind of something analogous. Anyone has a better analogy, let me know. So, Extend design guidelines. We made the decision, and this for us was very natural decision, but for many people in the HPC community may not have been that natural. That is, we want to start with state-of-the-art OO language technologies as a foundation. So we don't want to just go off implementing a new language from scratch, and we want to make this language accessible to people who are trained in languages like Java. We want to raise the level of abstraction where we feel confident that we can obtain optimized implementations, certainly by the 2010 timeframe. And you'll see some examples of that. That lock-based monitors, we're going to atomic sections. Threads, we're abstracting as asynchronous operations. Barriers, we're abstracting by something like clocks. There are challenges to get these right, but we think they're containable. But there's some other areas you can't just abstract away, and this goes back to what's happening with the hardware trends. The hardware is getting heterogeneous and parallel, the data access is non-uniform. We think it's untenable to hide that all from the programmers. So we're introducing new constructs to model this hierarchical parallelism and non-uniform data accesses, places, distributions. I'll talk about that briefly. We've benefited from all these people who've contributed design ideas by kind of mentally testing out our design space with different parallel programming idioms. What if you want to do data parallelism? What if you want to do message passing and so on? We really want to make our best effort on ensuring that every program has a well-defined semantics independent of the implementation. Many people involved here are familiar with all the details of the attempts to define and redefine the Java memory model, and we believe we have a level of abstraction that we can actually provide a well-defined semantics much more easily than what's possible with Java today. And at least for now, we are not. I mean, this is just to ensure that there's to scope this out. we're not taking upon ourselves issues such as reliability and fault tolerance, which do become important if you want to use this language for true distributed computing. We're assuming that this is going to be a dedicated system with a dedicated interconnect, and lower levels of the system will manage reliability there. Okay, so given all that background, what do we have? Try to cram everything in one slide over here. So let's see. We've introduced a construct called places. So a place, the idea is really an abstraction of a memory coherent unit of execution. So you do not have automatic coherence across places, but within a place you can have multiple activities, and those are assumed to be coherent. So if somebody wants to think about mapping them to different parts of a machine, they can certainly map it to an SMP, or if you're thinking coprocessors, you can map it onto a coprocessor and its local memory. There are different options over there. Then there are 4 storage classes. Some of these have appeared in past languages for the HPC area as well. There's a notion of a partition global address space. There's place local, so that's the local memory within a place. There's activity local. An activity is like a thread, but it's possibly lighter weight and has, we think, better higher level abstraction than Java threads. And then we also have these value class instances. This is really like final objects beyond final primitive types. They're immutable data. And for now, we see a great convenience in not tying them down to any place. They could freely be duplicated, accessed anywhere. You don't have to bind them to a place. Activities, how do you create them? You can have an asynchronous statement. We'll see an example of that. That you can also think of it as a one-way active message. There's asynchronous expression, which is like a future. And there are for each and at each constructs, which are good for iteration. At each goes across places, for each goes across iterations of some data structure. And we think of these both equivalently for HPC-like constructs like arrays, and maybe more object-oriented constructs like collections. These constructs would apply to both. And then finally, this is the hard part, of concurrent programming. How do you create all these activities? How do you coordinate them? So we have atomic sections, which we see as the replacement for monitors and locking. Conditional atomic sections, which we would confess right now is the trickiest part of the programming model, where you actually wait for a condition and then atomically do the action. And that is the only construct that can introduce deadlock. If you work in a subset of X10 without using that construct, you're guaranteed that your parallel program would not deadlock.
Or do anything interesting.
Well, yeah, right, exactly. But there are many people who can do, yeah, possibly, right. Clocks, which are generalization of barriers, and this is of interest to people in the HPC area, where they've worked with MPI, where they've had the notion of a single barrier, even though they were doing heterogeneous things. So it was kind of, you were simulating a heart, and there was a finite mesh simulation and a fluid simulation, and they both had the same barriers because MPI only gave you one barrier. Now you could decompose it and have different clocks. And force for getting the result of a future. So, okay, so don't have time to get into details. We do have internally in development about a 30 to 35 page of the language definition. And if people are interested, I'm happy to spend more time, walking through examples. But just as one example, I want to mention the same UMT2K example, which Evelyn also used in her talk this morning. This is a good example because it's one that the HPC community relates to. It's an unstructured mesh rather than a structured mesh. And but on the other hand, if you look at it as an object-oriented programmer, each of those elements in the unstructured mesh basically look like elements of a collection. There's none of that, dense array, for loop kind of indexing going on. So the way these applications work is you have the unstructured mesh, and you have a partitioning tool that's outside the scope of the language that attempts to, that partitions these elements in a way so that if you distribute these clusters of elements across processors, you get good load balance and you reduce the communication. So this is pretty well understood by practitioners in the field. And then what you do is you get this communication structure going, which is like a wavefront computation, except now it's going through the unstructured mesh. where each cluster is receiving an aggregate of inputs from one of its predecessor clusters. This is specified by a graph. So you have really collections and a graph data structure.